Seems like they move it on me every darn day. All right, everyone. Good evening. Thank you for showing up. Who'd like to start us off?
I just jumped on to listen in again if anybody had any more questions. So.
Okay.
Yeah, hello everyone.
Good evening.
Good evening. Just I have one question on 4.9994. What is the difference between question A and question B?
Okay. I'm sorry, what number? Because we only go up through 488.
994. 4.
Oh, there it is, 94. Sorry. Okay. So question A is asking you to create a quantile plot, which we've done before in previous exercises, and I can show you how to do it again in SAS. And then question B is just asking you for the correlation coefficient and the p-value for that plot, which you get out of SAS if you just ask it to do inset statistics. So for instance, if we go to task and utilities, you can see my screen, correct?
Okay, yes.
Okay. So in task and utilities, under statistics, there is distribution analysis, and distribution analysis is where we get QQ plots.
Okay.
So if we double click distribution analysis, and then obviously you have to, load the data file. I'm going to use a different one because I don't want to give you the actual answer. So I'm just going to
okay.
what I've got. And then, you pick the analysis variable. So for me, I'm going to just pick number and family. And then under options, you can leave the histogram on, but you don't need it. So you can turn that one off, but you definitely need to check for normality. So that's where you want the normal quantile plot, right? That's what it's asking for. So you click on the normal quantile plot. And then here it asks for add inset statistics, and you click on that. And then once you click on that, it gives you this little menu where you can choose which statistics go in that little inset box. Well, you can leave number of observations, you don't really need it, but what you definitely need is the goodness of fit test, and that will give you the correlation coefficient and the p-value. So that's all you need, and if you run it, now mine of course is going to look weird because I have a terrible set of data that I'm running this on, but so there's your QQ plot, and then here's your little inset statistics. The normal test statistic is your correlation coefficient because it's basically running a test on the whether or not it's normal, right? And so this is your correlation coefficients telling you how closely the numbers, basically the dots line up to a straight line. So there's your correlation coefficient, and then here's your corresponding p-value.
Yep. I think I have this. So what about A?
This is A. A is just the chart. A is just show me the picture, and then B is, tell me that you understand that this is correlation coefficient and this is your p-value.
Oh, okay. So we can send only one picture, right?
Yeah, you only need just this one picture for both A and B, and then in B, of course, you just need to state that, this number is the correlation coefficient, and this number is my p-value, and then I think it asks you to interpret it. Compute it, and then comment on the degree of fit. Yeah.
Okay. All right.
And like any other correlation, right, we're looking for something as close as possible to 1. Because in this case, their QQ plots are always positive. You always have a positive slope. So you don't look for anything close to 1 or -1. Normally, when we're talking about linear correlation, you could have a negative correlation that has a correlation coefficient of -1 would be a perfect correlation. But when we do QQ plots, because you're squaring things, you're always getting positive values, so you're always getting a positive correlation. And so you're really just looking for that test statistic to get as close as possible to 1, right? The closer it gets to 1, the better it fits. And then the p-value tells you how statistically significant it is.
All right, I understand it now. Thank you.
My pleasure. What else?
Dr. McBride, I sent you my draft yesterday, I think while the class or after the class.
Yeah, that sounds about right.
Okay. Did you receive that?
I did. Yeah, I've got like 5 of them sitting in my inbox that I have
Okay.
to go through.
Cool. Thank you.
Can you go over 4.88C?
B, did you say B is in Bravo?
C is in
Oh,
cat.
C. Okay. So the thing to remember about C is if we want to be strictly between 8 and 14, then that means we really only want the binomial values 9 through 13. Because that's, you know, what it means to be strictly greater than 8 and strictly less than 14 when we're dealing with a binomial distribution. So let me do this. And then we can draw all over this and talk about what's going on. Okay, so when you're doing, you know, binomial distributions, if you're looking for this, that really means you want the probability of 9 plus the probability of 10, right? Plus the probability of 11, plus the probability of 12, plus the probability of 13. And you'd have to figure all those out individually, you know, with the formula and add them all up. But we can do the binomial CDF function either in SAS or in Excel. And if you do the CDF function, that always gives you the probability of 0 through X, and you just choose an X. So in this case, you would do the binomial CDF of 13, and that would give you 0 through 13. Then you would do the binomial CDF of 8, and that would give you 0 through 8. And can you see that if you subtract this one from 0 through 13, you're going to be left with 9 through 13. So that's basically what you'd have to do for that one to get the exact one, right? So they ask for the exact and then the approximations. So when you're doing the exact, you have to do 2 binomials and you have to take their differences. So in SAS, right, we have to go to our probability codes and we have the binomial PDF and we need the binomial CDF. Now for this question, our sample size was 20 and our probability was 0.5. The first one we need is 13. So we run that. And the CDF of 13, right, is 0.94234. So this one, there it is, equals 0.94234, because that's 0 through 13, as you can see the 13 right there. And then if we go back to the code and we change it to 8 and run it, then we can see that 0 through 8 gives us 0.25172. So of course this minus this will be our answer, right? So 0.94234 minus 0.25172, that will be our exact answer. Now, the normal approximation with the continuity correction. So remember when we did the previous question, right? When we just did part A normally, we got a really, you should have got a really bad approximation. But then when you do it for 4.5, it gets better, and that's that. And I talked about this in my video. We're doing it. It's what's called a continuity correction. It's because the binomial distribution is a discrete probability function, right? It comes from discrete numbers. You get 3, 4, 5, 6. There's gaps. Whereas the normal curve and the normal probability distribution is a continuous distribution, and so you're filling in all of those gaps. So if you have a normal curve and you're using it to try and approximate this binomial, well, there are all these gaps. And so it's overestimating things because it's giving you all of this area instead of just these bars added together. So we do that correction by kind of rounding down by a half. And so if we want to get the correct answer for this one, we don't want to go, we don't want to do the normal curve at 14 and the normal curve at 8 and take the difference in between those two. We want to do like 13.5 and 8.5 and do the difference in between those two and see how that works. And that should be a lot closer. And you can play around with it and try and get the best one. But usually the idea is we know that binomially speaking, right, with the binomial curve, we're getting 9 through 13. So we don't want to just go to the normal curve and go, all right, give me all of the area between 13 and 9. Of course, I'm making this up. I have no idea, where they would fit on the curve, but we don't want all that area because we're getting too much extra. So instead, you can play around with it. You can try 13.5 and like 8.5 and see how close that is. Or you can try 9.5, right, and 12.5, and you can go back and forth. But basically what we normally do is we take these endpoints and then we round off of them, right? So y is supposed to be less than 14. So instead of taking our probability curve all the way up to 14, because that's what it means to be less than 14, we're going to stop it at 13.5. And instead of taking the bottom of the curve and going all the way down to 8, because that's what this says, right, to go between 8 and 14, we're going to come up to 8.5. So ideally, 8.5 to 13.5 should be the best approximation.
Okay, thank you. I appreciate that.
Yep.
That explained it a little bit better to me. So.
Okay, I got a question here. Does it have to be like a 0.5 interval, or like, let's say 13.8 or something? You cannot do that?
Well,
Yeah.
I mean, here's the honest truth. We don't do this ever in the real world. Nobody approximates the binomial with the normal curve, because why would you when you can get the precise answer out of the binomial?
Yeah, okay.
Right? So this is really more of a teaching tool than anything else. And so it turns out that, yeah, you can finagle the decimal points a little bit here and there and get closer and closer approximations. But that finagling is always going to change depending on, so right now we're doing 8 to 14. It might turn out that 13.7 and 8.2 gives you the best approximation. But if we went between like 10 and 15, then it might end up being 9.8 and 14.2. So the endpoints are going to shift depending on where we are on the curve, because it's all about how much error there is for each little bar in relationship to the curve. So normally we just pick the midpoint. We just always go basically in a half step from both, right? So continuously we would find all of the area from 8 to 14. But in a discrete world, we end up only getting 9 through 13. So to make up that difference, we, instead of in the continuous world going all the way from 8 to 14, we shrink it down and go 8.5 to 13.5. And that gives us a pretty good approximation. And it's really just a learning tool. It's really just kind of pointing out the fact that discrete distributions and continuous distributions are, two completely different things, but they're similar enough that we can kind of tweak them and play around with them. I mean, they're still probability distributions, so they still have a lot of things in common, but there's a huge difference between a discrete variable and a continuous variable, and you would obviously use the right thing with the right variable. And really the only reason why this is still being done today is as a teaching tool. Now, way back in the old days, before computers and before it was really easy to calculate binomial CDFs, right? Because you would have a calculator or whatever to do it for you, and you had to calculate all of these binomial things by hand with the formula and just, a calculator. It was a pain in the ass if you had a large range. Let's say you wanted to find the probability of being between, 7 and 700. Holy shit, you'd be there for, a month and a half computing all those things. But you could approximate it with the normal curve and get it with one computation. Now, granted, the computation for the normal curve by hand is a little bit more complex, but it's still relatively easy to do by hand. And so that was really the main driving force behind why we ever even did this. It was to allow us to do very large binomial CDFs when we, had to do them by hand. And then once computers came around and we could get these things out of Excel and whatever, and gosh, every TI calculator out there can do it for you, this approximation tool was no longer necessary, and it really just became a teaching tool.
Yeah. So even if I change the 0.5 for like 8.5, 13.5, I get the same numbers at the like 13 and 13.5 has the same outcome. I don't know what's wrong with the SAS.
Oh, you're talking about if you do the normal curve, the normal stuff?
Yeah, with the normal, yeah.
Oh, it could just be that you're not seeing enough decimals of difference, I guess, maybe.
Yeah.
Let's see. So normal CDF, this one here, and we're going to have 13.5. The mean is 10, and the standard deviation is like 2.3 something. Do you have it in front of you?
Okay, let me see what the standard 2.23607, I believe.
Something like that?
Yeah.
Okay,
2.3,
close
yeah.
enough. All right, so if we run this one.
Okay, I think you may be right. So
Something's wrong with my code.
data is normal CDF.
So this needs to be.
It's not binomial, it's normal, right? You're
Yeah.
writing normal, yeah, okay.
So data normal. There we go. Let's try that again. What's wrong? Statement is not valid or is used out of proper order. Value of interest. Oh, I'm such a stupid. I need to do the other one. I keep forgetting that on this one, they want you to put the numbers over here.
Mm.
So 13.5 and then 10 and then 2 point, I'm just gonna put 2.3 for now. Yeah, there we go.
Okay, okay, I see.
So 0.93596. And then if we change it to 13, so let's remember it was 93596.
It's very close. Okay.
93596, and then run this. Yeah, 90394. So it is different.
Okay. Okay.
Can I ask a question that's in this range? So, you know, the PDF and the CDF is the difference, the probability density function and the cumulative density function. But in Excel, I'm thinking that this is where the true false comes in and like the norm.
You are absolutely correct. In Excel, true equals CDF, false equals PDF.
True is
CDF.
CDF. Okay. And so then the clue in the problem that you're trying to solve is if the question asks for, so I'm trying to, like, if we're using this 4.88 as an example here, you said to use the binomial CDF, which is the cumulative density function, because what part in that question is it?
Well, it's the fact that they want multiple probabilities, right? So the PDF is only used if you want the probability of one specific thing. So it said, you know, if it said, you know, what's the probability that y equals 9, then you would use the PDF with 9.
Okay.
Because they give you a range and they want y to be between things, and it'd be the same thing as if they just said y was less than something, right? So it's the same thing for part A where it wants y to be less than 5. That's going to be a PDF as well. If they wanted y to be greater than 5, that would be a PDF as well, but you'd have to do 1 minus it because the PDF is all, or I'm sorry, the CDF is always accumulating from 0 up to and including something, right?
Okay. When it says to the left, like, right, it's always that number or whatever.
Yes, exactly. So for part A where it says y needs to be less than 5, you would do in Excel, you would do the binom.dis, right? The binomial distribution, you would put in true to make it cumulative, and your number of interest, your x, would be 4, because to be less than 5, you've got to be 0 through 4. And so when you put a 4 in there, and then the mean and the sample size of 20 and the p of 0.5, when you put all that in and run it, it's going to accumulate all of the probabilities of 0 plus 1 plus 2 plus 3 and plus 4, and that's what it means to be less than 5. You don't include 5 because less than 5 means you stop at 4.
Gotcha. Okay.
Yeah.
Thank you.
Yep. What else?
Would you address 4.79 and question C?
Okay, what is the 90th percentile?
And if you would, from an Excel perspective, would be
Sure. Yeah, absolutely. Okay, so
that's what is the 90th percentile? It's the manic depressive patients. They've got a mean of 930 and a standard deviation of 130.
Yeah, so I always like to draw pictures with these, especially when I'm dealing with the normal curve, because it helps me just visualize what the hell I'm doing.
Mm-hmm.
And so I've got a nice, pretty little normal curve. And the mean, as you said, was 930.
Mm-hmm.
And then the standard deviation was 130. Now they say, what is the 90th percentile? So the 90th percentile is going to be some value up here, X. I don't know what it is, but
Mhm.
it's going to have 90% of the data values are going to be down here to the left of it, right? That's what it means to be the 90th percentile.
Okay. Okay. And so then it's going to be a number like, obviously it'll be out beyond the standard deviations, but it will be what is the 90th percentile of the mean square? So, I mean, is it going to be something like 1,000?
Right, exactly. It's going to be definitely bigger than 930. That's all we know
Okay.
at this point,
Okay.
right?
And it's not going to be, it's not, we're looking for probability or anything like that. It's going to be a
An
number.
actual number. Yep, an actual number. So in Excel, you have to do the inverse norm function.
Okay.
In SAS, it's the last one in our code for those of you that are doing it in SAS. But for Excel,
Is it norm.inv?
yes.
Okay. Norm or .s.inv?
Let's see. It's just going to be the norm.inv. So it returns the inverse of the normal cumulative distribution for the specified mean and standard deviation. Yeah, so norm.inv. Double click on that, and then the nice thing is it tells you everything you need. So it wants probability to the left. So we're looking for the 90th percentile, so we want 0.9,
Mm-hmm.
comma, it wants the mean, which was 930, comma, the standard deviation, which was 130, close the bracket, hit enter, and there's your answer, 1096.6.
Okay. Okay.
So your guess of 1,000 was pretty darn good, right? At least you got an idea, instinct-wise, you know where it's going to be roughly, right? Because even from just the empirical rule, we should know roughly where it is.
Mhm.
Because if we go one standard deviation in both directions, that's only 68%. But if we go two standard deviations in both directions, that's 95% of our data, which means we would only have 2.5% above. So that'd be the 97.5 percentile. So we know this answer lies somewhere between 1 and 2 standard deviations above. Well, 1 standard deviation above would be 1,060, right? And then 2 standard deviations would be 1,190. So we know it's somewhere between those two. And of course, it came out to 1,096. So it's right where we knew it should be, in between the two.
Yeah, in SAS we got 967. That's what I have in SAS, from SAS.
Yeah, I thought I got a smaller one in SAS as well. 0.9, 930, 130. Equals. What's this one? Returns the standard normal distribution. Nope, that's not what we want. Returns the inverse of the standard normal. Nope. Yeah, it's got to be this one. Returns the inverse. Normal cumulative distribution for the specified mean and standard deviation. Yeah, so we're using the right function. Did I put something in wrong? 90%, and it's 930
Yeah.
and 130.
I just use the equal norm invoice and just use the 0.9 in quotations, and I got 967.208.
Okay, okay.
Well, you have to tell it the mean and standard deviation.
Yeah,
Yeah.
I
So
did that.
0.9, 930, and 130. I don't know why we're getting two different
Yeah.
answers.
I had 930 1.28 times 130 over square root of 20.
Yes.
Oh, is this a Oh, I forgot we're doing a random sample of 20. Ah, that's where it is. It's the random sample of 20. So we forgot to change our standard deviation based on a random sample of 20. See, what I did is I calculated that would be the score if we were taking a sample of one thing at a time. So the standard deviation would stay at 130. But because we have a sample of 20, we have to adjust, right, our standard deviation, and our new standard deviation of our sample is 130 divided by the square root of 20. And then we have to put that one into the function. Now, you could, calculate that in your calculator and round it, but you could also just do 130 divided by SQRT 20, because that's the square root function in Excel. And there we go, the 967 that we got in SAS.
Yeah.
Thank you for pointing that out, everybody.
Yeah, thank you. Thank you.
Okay, so Amy, does the function, the norm.inverse function, you got a handle on that? That makes sense?
Yes, it does. Yes, it does. And it looks like I can actually do the square root within the norm.inv.
Yes.
Like you can do that.
Yeah, you can always do functions inside of functions in Excel. So instead of having decimal places and rounding, if you ever have to take square roots of stuff, just put in SQRT and then parentheses the number and just stick that straight into your function. And it can do functions inside of functions. It's a beautiful thing. And SAS does the same thing, right? So if we were going to do this in SAS, we would have to use the quantile function here. And if we want the 90th percentile, then of course we want 0.9, right? And we set the mean to be, what was it, 930. And then the standard deviation, we could set it to be 130 divided by the square root of 20. Oops, 20. And if we run this way, ta-da, 967, right? It does square root of 20 in SAS the same way it does it in Excel. It's kind of cool. So you don't have to do square root of 20 in your calculator, right? And do 130 divided by it and get this big ugly decimal and then ask yourself, oh, how many decimal places of accuracy do I need to carry? And blah. Nope, just stick it in SAS and it carries all the decimal places you want. And it gives you the most accurate answer possible. And same thing in Excel, you can put that square root right into it.
Okay.
Just know that for both functions, the Excel version and the SAS version, the probability, right, the P that they're asking for is always area to the left. So to be the 90th percentile, of course, we put 0.9. But if they said, what score puts you in the top 5%, well, then what would we put in for our p-value? And I'll open it to the whole class. If we want to be in the top 5%, what would our p-value then be in this function?
1 minus 0.95? No?
Close. It would just be 0.95.
0.95.
Because if we want to be in the top 5%, we have 95% below us. And so that becomes the p-value for the function is 95%, because it's always the amount of area below us, the area to the left, right? So this value was technically in the top 10% because there was 90 below and 10 above. And if they had asked it that way, right, what value puts you in the top 10%? Well, the top 10% is the same thing as the 90th percentile, and you would put in 0.9 into the function.
Okay, I got it. Thank you.
Yep.
I have a question.
Go for it.
On the final project, can you go on part 1 to see what we are supposed to do on part 1?
Yes, part 1, you're supposed to basically calculate basic means and standard deviations for each of your sets of data, and then you're also supposed to do a bar chart for them. So let me get the, where is it? Final project right here. Right, so it says describe each probability distribution in the given Excel file. Use histograms. You can really, I think bar charts are better. And numerical summaries such as the mean and standard deviation and their interpretations in your explanations. So to do means and standard deviations for probability distributions, you have to use the weighted variable. So here's my part 1 data. I've already loaded it in, and you can see that I used the clean data set that I put in the Google Drive for everybody. So here's families per parish, and then families per parish probability, and then freight probability, number and family probability. Because the original data set was horrible because, well, first of all, it had a bunch of extra crap at the top that if you tried to load it into SAS, it wouldn't work because the first row had a bunch of junk, and in order for SAS to load data, the first row has to be the variable name, and then the numbers have to start in the second row. And it didn't do that for either of the sets of data. So that's why in the Google Drive I have, the regular data set so you can see what it looked like, but then I have, that data set with the word clean on it, where I have cleaned the data set, i.e. make it so that you can load it. And then I also changed the names of the variables because they just had, like families, and then this was probability, and then this was freights, and then this one was also probability. So you had all 3 probabilities were named the same thing. So when you go to pick them, it's hard to figure out which one is which. So I renamed things so everything is clear. Okay, enough being said, I'm just pointing out some things that if you guys are ever doing statistical analyses on your own and you have your own set of data, these are just some things to keep in mind, that you always want to make sure that all of your variables have different distinct names and that the names mean something. Don't just call it X1 and X2. Give them names that make sense so that when you're running these programs and you have to choose the variables, you don't have to go, what the heck is X1 again? It tells you right there what it is, so you know which one to choose. Okay, so part 1, we need to do summary statistics, right? We need to do mean and standard deviation was one of the things it asked us to do for everything. So let's choose, and I just forgot what it was. This is 2, here's 1. 1 is in import, okay. So now go back to this and work.import, okay, very good. And we're going to just start with the first one. So we're going to put families per parish is the analysis variable, but if we ran it right now, this mean is based on just the values from the distribution. Families per parish had the numbers 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then they had their corresponding probabilities. So what 3.5 is, it's just the average of the numbers 1 through 9. That's not correct. That's not the actual average of that probability distribution. You have to weight those numbers, right? All of those numbers didn't show up with equal weights. They didn't have equal probabilities. So instead, you click on additional roles, and down here you have a weight variable, and you click add, and then you put in the families per parish probability as the weight, right? So we're going to look at families per parish, and they're going to be weighted by their probability. And now if we run it, that is the correct mean and standard deviation for that probability distribution. Now, if you go and do a histogram for these things, which is totally fine, but I'm going to show you the difference between the two and show you why I think the bar chart is better. If we run a histogram, again, it's work import, right? So it's that stuff. We're going to put families per parish, and again, we have to weight them. So families per parish probability, and then run it. It looks terrible. That's a terrible histogram because it just gave us, 4 things. Okay, well, families per parish has 9 data points, 1 through 9. So let's go to appearance and let's go to bins, and let's specify and make the bins 9 and see if that makes it look better. Better, but still not great, right? You got these little tiny ones here, but this is fine. I still don't like the fact that they're touching, because it's really not, histograms are supposed to be used for continuous data only, and these are discrete data values, right? Because there's gaps. So if you do the bar chart instead, and you do families per parish, additional roll, weight it by families per parish probability, right? And then run that one. Oh, I didn't, families per parish probability. Oh, it's under frequency, that's why. This needs to be under frequency percent. Nope. Oh, measure it by the variable? Oh, that's what it is. That's what it is. You have to measure it by the variable and then put in the probability here. There we go. And so now you can see that everything is, they're spaced out, right? There's gaps. So either one is fine, and neither of them looks great, and that's just because the data itself is crappy. But that's what I would suggest.
With that in mind, with Excel, can you comment on if there's anything to be aware of as it relates to weighting this? So it's, I think it has a better mean, is what you started off with.
Yeah, so in Excel, you can get the mean and standard deviation kind of by hand.
Yeah.
By dragging and calculating each column and then getting it that way, and so that's not so bad. Once you have the values and their probabilities, then you can insert a graph, right? You can insert a bar chart.
So are you saying that the weighted, the weighted factor of this will already be in those because I mean, I know that those functions, how to pull that stuff, but will the weighting happen a bit more automatically? Is that what I'm to understand?
Well, what I'm saying is that your you have to weight it by their probabilities.
Yeah, okay.
So let's see if this works. Yeah, I think that's off by 1, obviously. All right, so there are our 3 sets of data and their probabilities. If we wanted to, like for instance, do a histogram of this data, right? Then you have to be able to tell it its frequencies, and I don't know how. I can't remember off the top of my head how to do it.
I remember doing it, but I can't likewise, I can't remember it right now. Like I know that was, I don't think that was the bin limits, was it? No.
I don't think so. I think it's something to do with this stuff where you then put those in, I think. Yeah, it's something like that.
Okay.
And that should be, yeah, that should be your parish one.
Okay.
Yeah.
Thank you.
All right, what else?
Dr. McBride,
Yes, Nicole.
can you go over C and D on 465, please?
265. C and D. Okay. So C pictorially is this, right? We've got 150 and we've got 350 and we're looking for the area in between those two. So to do that, are you using SAS or Excel?
SAS.
Okay. So in SAS, we need to run two CDF functions, because basically what we have to do is we have to run the CDF function for 350, which gives us all of this area, right? Everything below 350. Then we come back. Thought there was a way to change its color. I guess it'll only highlight. Then we come back and we do the CDF of 150, which gives us all of that, right? And you do 1 minus, and it gives you the stuff in between. So that's what you're doing. You're basically just doing two of the CDFs, right? So we go down here to the normal CDF, which is right down here, normal CDF. The first one is we do 350. The mean was 250, and the standard deviation is 50. And since we're only picking one thing, our sample size is 1, we don't have to divide by the square root of anything. I mean, we're divided by the square root of 1, so we're just dividing by 1 and nothing changes. But we run this. And so 0.97725 is everything to the left.
Right.
Right, so all the stuff in the yellow is, do that and then make it black, and it's 0.97725. So that's all of that area. Then we're going to go back and we're going to change it to 150. Run it again.
Okay.
And that gives us down here, this area is 0.022750. So if we subtract, right, we'll get the leftover. So it's really just going to be that one minus that one will give you the bit in the middle.
Okay.
Is
And
this,
go ahead.
is this a bit of a trick question? Because both of those numbers are the two standard deviations from the left and the right. Do you see what I'm saying?
Yeah. Well, no, it's not a trick because you're absolutely right. If we go exactly 2 standard deviations above and 2 standard deviations below, which is what we've done, we know from the empirical rule we should have 95% of our data.
Right.
But if you do the math here, do you get exactly 95%?
I haven't done that yet. I was just thinking it was a trick question.
No, you get very close to 95.
Okay.
And that's because, as I mentioned before, the empirical rule are close approximations.
Okay.
So you'll see that you don't get exactly, right? So 0.97725 minus 0.022750, right? So 0, 12 minus 7 is 5. That's a 6 minus 2 is a 4. That's a 5. So you get 0.9545. So it's pretty damn close to 95%, right? It's 95.45%.
Okay, okay. I'm glad whoever asked that was that Nicole. Thank you.
So that's that one. And then part D is basically saying, okay, if we have the curve, and here's our mean of 250. If we go out some distance k in both directions, right? So this value here is going to be 250 plus k, and this is going to be 250 minus k, right? Whatever k is. Then the area in between those two marks, everything in yellow, needs to be 60%. Well, as you just pointed out, we know that if we go out 2 standard deviations, we get 95. We know if we go 1 standard deviation in both directions, we get 68. So we know that k is definitely going to be less than 50, right? Because if we want a full 50, you know, if we want a full standard deviation in both directions, so i.e. went up to 300 and down to 200, that would give us 68%. We only want 60, so it needs to be a little bit smaller. Okay, well, how do we actually calculate this value? We're looking for an unknown. You know, like for instance, we're looking for this x. We want to know this value. Well, if this has 60% in the yellow stuff, how much is left over underneath the whole curve? And this is not a trick question. If there's 60 in the yellow stuff, what's left over?
40.
Right. And because the normal curve is symmetrical, how much do we know for sure, right? How much is in this left tail?
20.
20, very good. So, where the hell is I always lose my cursor. It's so hard to see this little tiny black dot. This is 20%. Okay, so we know that we can use those inverse functions and find a value that has 20% less than it. We're basically finding the 20th percentile. So use whatever function you want to find the 20th percentile, right? If you're in SAS, then we're doing the quantile function, where this would be 0.2, right? The mean is 250, and the standard deviation is just 50. And we run this, and it gives us this value, 207.919. So that means that that x, right, is 207.919. Well, that's great, but that's not the answer they asked for, right? They want to know what k is. Well, that's easy because we can just do a little simple math, because 207.919 we know has to equal 250 minus k. Solve for k. It's that simple. Now, if we were going to do it in Excel, the only thing that would change is how we got that left-hand number, right? And that left-hand number is that same norm dot inverse, only now we're looking for the 20th percentile, right? And we have a mean of 250. And a standard deviation of 50. And there's that same number of 207.91, in this case 89, which would round to 919, right? And then you can use a little simple algebra to solve for k. Question?
42? Is it 42? 208
Yes,
minus-
yes, it's
it is.
42.
Ooh.
Yep.
Good, good. Thank you.
I have another question.
Yeah.
So on the final project again, which code we have to use on part 2?
Which code?
Yeah, on part 2.
Part 2, you're just finding a bunch of probabilities. So I don't care if you use SAS or Excel. I think it's easier in Excel because, you know, you can just calculate the probability with a simple function and then drag it and fill in the whole table, right? Because you have all these different values for all your judges, and you have to do the probability of, you know, an appeal, and then a reversal, and then a conditional, and all those are just simply with some real simple math and little simple functions, and then you can drag them and populate the entire table really quickly. So I would suggest doing those in Excel.
And it is said to prepare a report summaries. So how do you want us to do this report?
Are you talking about part 3 of the report?
No, 2, on part 2.
Well, you would just basically copy and paste your tables, right? And then rank the judges based on what you think matters, and then discuss how you came about that. So discuss how you determined all of their probabilities, and discuss how you determined their ranks, and why you did it the way you did it. Because there are really two different, in my opinion, I think there are two different ways that you could rank the judges, that you could make a strong case for ranking the judges. And I'm not going to tell you what those two are because I don't want to bias you. I want you guys to think about it. I mean, you're obviously looking at judges, and you're looking at the probability of, you know, their cases being appealed, the probability of their cases being reversed, and then the probability of a reversal given an appeal. So conditional probability, and then the probability of cases being appealed and reversed in the 3 courts. Is you're basically just doing kind of probabilities of the whole group, not judge by judge. So that's what part 4 is. But the first 3 is, you know, information on each judge, a probability of any time you know, they rule, it being appealed, and then anytime they rule, it being reversed, and then anytime they rule and it's been appealed, what's the probability that it then goes on and becomes reversed, right? So those are the 3 probabilities you're calculating for the judges. So you could really make a case for ranking them really 3 different ways. In my opinion, I think only 2 of them are strong opinions. It would be pretty obvious, I think, that one of them would be the weakest way to rank it, but you could still make an argument that way, and I would not take points off if you rank them that way, as long as you described how you ranked them and why you chose that way.
Okay. Yep. Thank you.
Yep. All right, we're at 5:29. So any last minute questions before we go?
Will we
Course,
have a meet session? Oh, I'm sorry.
go ahead.
Will we have a meet session next week?
Next week we have the same 2 times. Yes, we have meet sessions next week, but next week the meet sessions are only there. I mean, I'll answer questions, but the main thing that we're doing next week is you guys are presenting your scenarios for part 3.
Oh, that's-
So this part 4, this presentation of your part 3, is basically what you'll do in the meet session next week. Is you'll just briefly describe what you're doing for questions 1 through 5, to make sure that you're just on the right track, that you have the right kind of data and everything would work out properly.
Okay.
Somebody else said something like they had a question.
Yeah, course evaluation, that's what I said. Just let's make sure, yeah, you send email. We have
Yeah.
to- yeah, evaluation, yeah.
Yeah, I sent it out, so hopefully everybody will fill those out, please.
Yep.
And I'll
Just
send another
employ-
email out to remind everybody about what we're doing next week as far as presentations are concerned. They're not. I'm not looking for a formal presentation. I'm not looking for, a PowerPoint presentation or for you to even share your desktop and show us anything. It's literally just this is my research question that I want to investigate. These are the variables that I'd like to collect. This is the kind of data that I'd like to collect. This is how I would go about collecting it. And then this is how I'm thinking about analyzing it. And then we'll sit there and discuss in a group and go, okay, well, if you did that, your data really wouldn't be continuous. So that's a bit of a problem because part 6 is supposed to be tied into questions 1 through 5. And so you need a continuous variable. So maybe if you tweak your research question this way, then the data you get will be continuous instead of discrete, and then everything else can remain the same, but now you'll have continuous data and everything will be fine. So it's kind of that kind of thing, because this whole thing is just it's a thought experiment. You're not actually doing anything. You're not actually collecting data. You're not doing any of this. And even as far as number 6 is concerned, where you're calculating probabilities, you're creating the scenario for those probabilities. So you're basically recreating what happened here in questions 1 and 2, where you're creating a scenario where you're getting a value that is greater than something or less than something or in between something, and you're giving it some sort of context, like they did with 4.7, where they said, oh, these numbers came from the college boards and they have a mean of this and a standard deviation, blah, 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 right? But you're just making all that crap up, and you're also making up what to test. When it says find the probability the continuous random variable is greater than a specified value, well, that specified value could be you. I mean, you could choose anything, right? So you could say, okay, well, I'm going to calculate the probability that it's greater than 200 based on blah, 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 blah. Or I'm going to calculate greater than 30 based on a mean of this, right? So everybody's numbers are going to be completely different based on their scenarios and the numbers they want to choose. But the idea is that those numbers would come from the data that you're describing in 1 through 5. So that's why you want to pick a variable for 1 through 5 that is continuous, so that you could, in essence, run the real things in number 6 if you actually had the data, the real data for that variable. But this is all a thought experiment. You're not collecting anything. You're not, doing a real formal anything. It's just getting you to start thinking about the whole process of developing a research question, figuring out what kind of data you would need to gather to look at that research question, and then how you would analyze that data, because that's what you're going to need to do for your dissertation, which is why I keep telling everybody, if you can, please try to make this scenario match your dissertation, right? Don't just make up some arbitrary scenario, some arbitrary research question with some arbitrary variables that means nothing to you. Try and make it actually matter and match your dissertation. So it'll get you thinking about how you can attack your dissertation. And even if your dissertation is not going to have a continuous random variable in it, you're not going to be collecting that kind of data, that's fine. Still use research questions and scenarios that match your dissertation. We'll just tweak it enough so that the data you get would be continuous, and then when you do it for real, you can go back to the other way, and use the actual data that you wanted. So does that make sense to everybody?
Yep.
Yeah.
Yes.
Awesome. Okay, we're 5 minutes over, so let's get the hell out of here and go enjoy the rest of our nights.
Thank you. The recording will be
Will you be only on Wednesday?
Thank you. See you tomorrow, or see you next week.
Thank
Okay,
you.
bye.
Thank you.
Bye.
Thank you. Bye, everybody.
Recording.